The physical limits of planar lithography forced solid-state storage into three-dimensional architectures. In 3D NAND, memory cells are stacked vertically, requiring deep channel etches filled with tungsten metal to form word lines. This metallization process relies on the chemical vapor deposition of tungsten hexafluoride. As layer counts scale from 128 to 232, tungsten hexafluoride consumption per wafer increases by approximately 45%. Global demand for electronic-grade gas is projected to scale from 4,100 metric tons in 2022 to over 7,300 metric tons by 2028. This represents a compound annual growth rate of 10.1%. At 300-plus layers, vertical aspect ratios exceed 100 to 1. These extreme geometries require extended deposition times. The resulting process inefficiency increases the gas-to-solid waste ratio, compounding volumetric demand. While raw tungsten ore is abundant, the capacity to purify it to electronic-grade standards is highly consolidated. The top three manufacturers control 78% of global purification capacity for 5N5 purity tungsten hexafluoride. These firms are South Korea's SK Materials, Japan's Kanto Denka, and the United States-based Merck. South Korea and Japan combined control 71% of global high-purity synthesis capacity. This concentrates the midstream supply chain within the East Asian Semiconductor Corridor. Chinese domestic capacity, led by the Liming Research Institute, is expanding rapidly to support domestic fabs like YMTC. However, export controls and strict qualification barriers prevent this capacity from easing Western supply constraints. The high-purity chemical corridor remains an effective oligopoly. The transition from raw ore to electronic-grade gas involves compounding material losses and extreme chemical hazards. The cumulative material yield from raw tungsten concentrate to packaged gas is approximately 50%. Half of the starting tungsten is lost or recycled during processing. Direct fluorination of tungsten powder requires highly corrosive elemental fluorine gas generated on-site. This step introduces severe operational hazards and localized supply constraints. The final fractional distillation step is the most capital and energy-intensive phase. It suffers a 25% yield loss to eliminate transition metal impurities down to subpart per billion levels. This extreme purification is necessary to prevent resistance spikes and gate oxide breakdown in 3D NAND devices.